Hypothesis of induced low entropy for fusion devices, a configurational key instead of the Lawson's criteria. An interesting fact. In the 1930s, both Rutherford and Einstein publicly called the idea of obtaining energy from the nuclear fission a utopia. They had their reasons for that, but just 30 years later, the first nuclear power plant began to provide electricity. The essence of the evolution of fusion machines in the increasing complexity of their systems, the growth in the number of controlled parameters, and the precision with which these parameters are maintained. Algorithms also become more complex. For example, following the evolutionary path of tokamaks, we see that feedback systems for magnetic fields were introduced. Magnetic field configurations become more intricate. All this to suppress plasma turbulence more effectively. In essence, this means preventing the growth of plasma entropy, which in language of Lawson's criteria is called confinement. Here lies the key point of my hypothesis. The main enemy that all fusion approaches fight against is the growth of entropy. Essentially, these measures reduce the degrees of freedom of the reaction medium. For example, plasma in space. Scientists are diving deeper into this fractal rabbit hole, but fail to see the obvious. While studying plasma instabilities, they already control individual vortices and even subvortices, and so on. Now we come to the next logical conclusion of my hypothesis. If we extrapolate their efforts into the future, we arrive at ever smaller scales of control. And the smaller the scale of control, the more effective the control of the medium, plasma. This is in essence an attempt to induce low entropy through parameter control. Main principle of the hypothesis. The more parameters we control, and the more precisely we do so, the lower the required input energy for fusion. This principle works at all levels of the process. For instance, if we control the spin and energies of nuclei, this increases the probability of quantum tunneling and fusion. By adding new parameters, we increase efficiency. Let's look at how this works in the laser fusion approach used at NIF, National Ignition Facility. One stage in the evolution of the experiment involved improving the precision of the spherical symmetry of the fuel pellet. This led to more uniform plasma compression, which in turn reduced turbulence and the growth of plasma entropy. An even more significant example, by using a hull room, 2 additional degrees of control were introduced, changing the laser wavelength from ultraviolet to X-ray radiation, and achieving a more uniform distribution of laser energy across the surface and into the depth of the pellet. All these improvements are connected with uniformity, precision, and the use of shorter laser wavelength, which are directly related to the characteristics of low entropy as a concept. But the most important thing is that, in scientific terms, the mentioned measures actually reduced the required input energy by a factor of 10. Yes, that's right. Even though the total laser pulse energy was increased, only about 200 kilojoules of energy in the form of X-ray photons reached the pellet surface, while the output energy reached about 4 megajoules or more. That's how the ILE hypothesis works. Think about it. This is what most tech bloggers have missed. Those who keep repeating, with sour faces like parrots, the same old jokes about 30 years and only 1% Q. In the next video, I plan to analyze the NIF experiment separately in the context of my hypothesis. What advantages, what advantages it has over other approaches and what problems remain. But for now, let's return to a more formal explanation of ILE. So, these examples demonstrate how increasing the number and precision of control parameters can reduce the required input energy. In the NIF experiment, another important point: the smaller the scale of control, the higher the efficiency of the reaction, which again remind us of entropy reduction. Extrapolating further, we reach manipulation at the molecular, atomic, and nuclear levels. Reducing in particle degrees of freedom at this level leads to collective quantum effects, tunneling, and even the case where a particle receives energy seemingly from nowhere, according to Heisenberg's uncertainty principle. The fewer degrees of freedom a particle has along one parameter, the wider the range of possible states along another, i.e. its energy. A particle receives energy not from the outside, e.g. not by absorbing a gamma photon, but as a consequence of the configuration of the environment. Let's continue the analogy and recall Moore's law. The denser the transistors are packed in a unit value, the more energy efficient the computation becomes. Please keep that in mind. The more energy efficient the computation becomes. In my complex hypothesis, we will eventually reach Shannon entropy and information theory. An efficient algorithm is also an energy efficient algorithm. It occupies fewer lines of code or executes faster. Now, if we apply the principle of my hypothesis to quantum objects, we arrive at an even more intriguing logical step. By controlling a large number of wave functions of the objects within a quantum system, we can influence the resulting wave function that defines the probability of nuclear tunneling for fusion. Think about it. Isn't that beautiful? The stronger we control the parameters of wave functions, the more efficient and more probable the reactions become. A new fusion device will include many methods of precise environmental control. The fuel pellet itself